Structuring systems, an application of basic structural modeling. This is the part 3 of this series of videos about structuring systems and basic structural modeling. Incorporated some feedback I've received from the first 2 videos, and if you've been watching this series, the videos will be improved as we go along. So the introduction video that's also on the YouTube site shows you how to get to my website, which has a lot of background information about the structuring systems activities that are discussed in this video. This is a link to my Twitter account. The main site has a lot of background information. It has document reports about that describes the activities. It also has mathematical code that goes with the SAGE math system. We'll have some of that mathematics will be discussed today, and have a little bit more as we go along. So the basic structural modeling project overview. I'll introduce the slide content that's been reorganized a little bit. Fundamental concepts, we'll go over those again. And then the general process steps. I've reorganized these a little bit so that they're easier to understand, more modularly associated with each primary step. And then process steps, which we'll touch on lightly today, but not finish up very much at all. And then, of course, process summary and conclusions. So this particular problem is structuring a system, and what we're doing is we have taken 19 cities that are in an unknown, unordered state, and we are going to order them into a system, and that is essentially a very basic fundamental system ordering process that we address here. We pick 5 cities at random because we really have no information about them, so we just randomly pick some and start collecting the information. Then we collect 5 data points each from those cities. So 5 times 5 will have 25 data points that we actually empirically collect. We go find out that information. Then we perform an analysis to order the cities, and then we use inference to limit the amount of empirical data that's needed. And the inference, basically in this case, is used to limit the cost of collecting empirical data. And then we go through and we select 5 more cities, order those cities, and this city ordering that we're talking about right here, this is the operation that's the subject of the design of this particular activity. We're in the conceptual design phase right now, and ordering the operation is the subject of this conceptual design. Now then we perform the inference operation. Of course, this is Warfield's approach. Now Warfield's approach, he just talked about essentially the operation itself, not how to fit it in with a larger over large scale type of problem. So a secondary type of design for this activity is to kind of explore ways that the inference and the basic structural modeling mathematical techniques can be incorporated into a complete problem solution process. And we take 5 more cities. Now these cities are actually selected one at a time, and then we wait until we get 5 of them, and then we order that. Then we perform the inference operation. So we select 5 more cities here in this group, and then we order them one at a time, but we wait until all 5 of them are done to perform the inference analysis. We won't get to this part today. That'll be later videos. And of course, we need to understand how to select the city with the highest inference potential. That's something that we'll also need to consider in our design process. And then we gather empirical data about the city and then order them, and then of course perform the inference operations to actually finalize and complete the structuring of the system. So our fundamental concepts of basically we're operating on the fact that there's 3 types of truth that we need to consider, and we create an approach that uses the same computational system. Formal truth basically has Boolean algebra, has computer systems and in some mathematics systems has a different symbol set, has a different type of mathematical approach, and we create an approach that uses the same computational system. It's basically the original algebra that Boole used, and we simply use a couple very simple transforms within the SAGE math system to help us work with those. Then we developed an abstract relation type which integrates the truth operations. The abstract relation type has three basic spaces: has a marking space, a value space, and an outcome space. And the marking space supports the formal and factual truth representations, and then the value space supports the value truth. And of course, it's based on the system structure and the arrangement of the components of the system. So here's a description of these types of truth. These slides are available on my website, so if you can't read them in the video, download the slides from the main website and you can read the content there. But formal truth is basically based on formal sentences, factual truth is based on the state of the real world, and value truth is basically a combination of both formal and factual truth. And it also includes culture, ethics, and value judgments of human beings and experts. So, and systems engineering is really about optimizing very complex systems. So the value truth is very important in systems engineering and systems science. Here's more detailed examples. But essentially what we have is, we look at this and the type of truth is known by experience. For formal truth it's no, for factual truth is yes, and for value truth it's sometimes yes and sometimes no. So we really want to know about the real world, so we want to know factual truth, but we want to also include formal truth because of its certainty and its ability to translate this to mathematical operations. And so when we combine factual truth and formal truth, we're diluting the certainty, but we're also gaining some efficiencies and abilities to look at larger types of systems using mathematics. And essentially we can see that it's required to validate the inferences. A proof is necessary and sufficient. This is where the mathematics comes in. And for factual truth it's observation data and predictive success. So we reduce the amount of effort it takes in the factual truth to validate it by including the formal truth mechanisms. An overview, a high-level conceptual overview of an abstract relation type. Really has the three spaces, as the marking space, the outcome space, and the value space. And any of these spaces can has one or more matrices within them. So we show multiple value matrices in the value space, but marking space and outcome space can also have multiple matrices. Abstract relation type basically is formed around Warfield's idea of a language that has three equivalent components. That's the prose description, the graphics description, and the mathematics or computer representation. And these are proposed as model exchange isomorphisms, meaning that you can take a problem or a system that's described in prose and you can translate that to a graphic representation without loss of information, and you can get the system represented as a graphic. Or if you have a graphic representation of the system, the model exchange isomorphism allows you to change that to a mathematics representation without loss of information, and you know that you're representing the same system. So this allows you to take a system and represent it in three different forms, which increases the communication and the communicatability of the system. Not many people, some people are very, very good with mathematics, other people are good with prose, most people are very good with graphics. So you can use these different forms and communicate to a much larger group of people about your system in a precise manner. So system structure, basically the authors have developed concept of systems concepts, and we use our system concepts basically in two different modes. We use them in a design mode where we're designing things, or we use them in a discovery mode where we're discovering things. So discovery mode is like Kepler discovering the solar system. He knew the planets, and he discovered the relationships between the planets. And the design mode, of course, is like John F. Kennedy saying, okay, we're going to put a man on the moon by the end of the decade. Okay, so we knew what the relationship was, put a man on the moon by the end of the decade, and we had to design all the object systems, facilities, and so forth to achieve that relationship. In this particular case, the graphics that we're using down here in the discovery mode. Most all systems graphics, especially systems engineering graphics, are used in design mode and design communication. So really need to make a clear distinction about the graphics and understand here that we're applying them mostly in the discovery mode. They can be applied in the design mode, but we are right now focusing on the discovery mode area. So system structure, a system is a relationship mapped over a set of objects. So we know the cities, and those are the objects. We know the general relationship, which is north of. We must discover the specific relationship between each city pair. So that's the objective of this process, is to actually discover the relationship between each city pair. General process steps, a number of these we're going to go through steps 1 through 4 today in a little bit more detail. And these particular parts, of course, is to identify the cities and create a matrix for the analysis piece, which is basically the marking space, and collecting initial empirical data, and then analyzing the order of the cities, and then conducting inference analysis. And we've added more to the slide deck to detail the discussion on the inference approach. So here's our beginning configuration, the marking space of the art. Essentially, we have 19 cities, and we have no information about these cities, no empirical information. So yellow 0 means this is unknown. So this says city 2 is north of city 1. Well, we don't know. We have no information about that. City 4 is north of city 1. Well, we don't know. We have no information about that, so it's a yellow 0. Notice that on the diagonal, all of the zeros are backed by a red. A red 0 means false. So what we know here is that city 1 is north of city 1. Well, we don't have any empirical information, but logically we will not allow a city to be north of itself. Where city 6 is north of city 6. Well, no, that's false. Just logically we won't allow that. So that's what this particular beginning configuration is. Then we collect the empirical data, put the empirical data, and you can see it's just randomly scattered. So let's look at this. City 2 is north of city 1. Yes, that's a green 1. And then we'll say city 1 is north of city 2. Well, no. We know that's false because city 2 is north of city 1. And this relationship is symmetric. So now let's look at city 5 is north of city 1. Well, no, that's false. So we know that city 1 is north of city 5. So that's true. You can see the symmetry of these two, 9 and 10, and 10 and 1. So they're across the diagonal. This is essentially a symmetric layout. Then we start swapping these columns. So what we really want to do is we want to move the green ones and put them all down the lower triangular, and we want all the red zeros to be in the upper triangular. So this is the ordering operation that we're looking at here, which is the point of our design. we need to design computer code or a computer approach that will allow us to automatically do this structuring process. So we move through here, and we can see, let's just look at the top rows. This is a good strategy to look at the top rows and then just make sure that the green one, so this green one we want to move down. Okay, and then this green one we want to move down. That's 2. Yes, right there. We want to move it down. And then we have a whole set of greens over here, so we want to move those down. We have a whole set of greens here. We want to move those down. But as you can see, the top is stabilizing now. And the 11 at the top is all zeros. And then there's a 1, 1. And so the top row is going to be all zeros when we're completely finished. So here's 8, it's got all zeros, 7, it's got all zeros, 17, 8, and 19. They all have all zeros in the rows. So these are candidates to be at the top when we're done, but we're starting at the top and kind of moving down with this pattern. So you can see here, again, we're just moving down. Now this is stabilized. We're not moving these up here. We're moving down this way, taking these green ones and moving them into the lower triangular by swapping the rows and columns. That's what's going on here. You can generally see that. So 11 and 2 and 3 are still up here at the top. And here's the only green one we have left is right there. And now we've got all of the green ones in the bottom. All of the red zeros are in the upper triangular, all the green ones are in the lower triangular, but we still have the same system, same objects, same relationship. It's just in a different configuration. And that's the objective, is to actually find the system configuration that meets the relationship. And then we do the inference. Now that we have this ordered data, we perform the inference operation and get these additional ones. We know through the inference operation, which is a calculation, that these inferences, these ones, are also true. And we'll discuss the inference steps. So the inference process steps basically were detailed by Warfield in his books. You create a matrix D from the empirical data. Then you create an identity matrix, which is a well-known mathematical object. And then you create M, which is a reachability matrix, by adding D and I. And then using Boolean operations, you multiply M times M. So you're really multiplying this matrix times itself until M doesn't change. The contents don't change. So this is a technique that was developed by Harari and others to actually show an inference type of technique mathematically over a group of objects that have the correct types of properties. The key problem, of course, is the Boolean operators. There's not many computer packages today that support the Boolean operators, and in the earlier work on this project, which is documented in the problem report and the conceptual design report, we talk about Sage and how we use Sage to support Boolean operators, and also Octave, and how Octave supports Boolean operators, but Sage was a better mathematics package, so we chose it. So here's a layout and a picture of the matrices, and these are actually in the worksheet, the Sage worksheet that accompanies this week's material. But this is the structural matrix. You can see the ones in here that are, then everything else is zeros. And the identity matrix is simply a matrix that has all ones on the diagonal. That's over here. And then we add D and I together, and we get the D matrix with all ones on the diagonal. And we use the decimal types of operations within Sage to do the computing of the inference, but then we have to change that decimal to a Boolean. So we define a decimal to Boolean mapping, which we use to configure and change the matrices so that it works in this particular operation. So our general process steps: we've identified the cities, and we've created a matrix, so that's done. We collect and enter initial empirical data, that's done. Analyze and order the cities, that's done. And this is the activity. The ordering the cities is one of the major things that we're designing for our software code. We're just discussing it now, the requirements. And conduct inference analysis, that's done. Of course, how to actually do the computation in the computer code is also going to be part of our design process. So we have these other things left to do, which is, of course, then collect another set of empirical data, which you see here in green, and we'll move through that. And you can see things are stable here at the top. He's not moving very much at the top. We're taking our greens and moving them down. The greens over here, we're moving them down. So that's the idea, is to actually move all of the greens, all the ones actually, because we have greens and blues, move all the ones into the lower triangular. And you can see that's happening. So we only have 2 left here. Okay, and now we're ready for the next shot. So that's basically going to be the end of this particular video presentation. But what we're doing is looking at what we need to do operationally to move all of the ones into lower triangular, and that's basically swapping rows and columns. That's how we're doing this. That's the function. And then integrating the inference also into the operation is also very important. And then after we've got these all ordered, of course, you can see we'll go to the next one. The next inference set brings in a lot more blues, and we're filling in a lot more here that we know that these are true statements. And of course the statement is city 11 north of city 2? Yes. City 11 north of city 15? Yes. That's how you read this that's the prose that you read with this mathematical structure in this graphic. So we'll have more videos in the future.